Welcome to another episode of the ASEF podcast. So far, we have explored the fields of physics, computer science, biochemistry, and robotics, and today we will be talking with three ASEF professors about mathematics and its applications. With us are Professor Mohar, who is a professor of mathematics at Fraser University in Canada, Sara Kališnik, who is a senior scientist in Department of Mathematics at ETH Zurich, and Andrej Bauer, a professor of computational mathematics at the Faculty of Mathematics and Physics at the University of Ljubljana. Thank you all so much for joining us today. First, I would like to ask you if you can briefly introduce yourselves and tell us where you studied, for how long you've been in the field, and maybe something about your current research. Please, Andrej, you can start.
Hi. Hello. Thanks for inviting me. I studied my undergraduate mathematics in Ljubljana. And then after that, I went to the School of Computer Science at Carnegie Mellon University in Pittsburgh, in the US, where I studied pure and applied logic for 6 years. This was at the end of the 90s. And then I returned in 2000. I spent a half a year also in Stockholm, but then I returned back to Ljubljana, where I am now a professor of computational mathematics. So you can calculate how many years that has been. It's been many, so more than 30 now, I think.
So I'm Sara Kališnik. I just like Andrej, I did my undergrad in Slovenia, the University of Ljubljana. So I actually also started my Ph.D. in Slovenia, but then very early on, I realized that I wanted to do applied topology. And at the time, nobody in Slovenia did applied topology. So I talked to some professors and they encouraged me to try to apply to American universities where more people in this field work. So I ended up applying. I actually only applied to two places, UPenn and Stanford, and I was lucky I got into Stanford. And then I did my PhD with Gunnar Carlson, who was sort of the person that I really, really wanted to work with. And then after the PhD, a string of postdocs started and a lot of moving around. I think I calculated it in the last 10 years. I moved around 8 or 9 times. So first I was in Boston for 1 year, and then I did a postdoc at Brown University in Rhode Island, and after that another postdoc in Leipzig at the Max Planck Institute, and then I returned to the US to be an assistant professor at Wesleyan University. And then, so I had a two-body problem, which made me move my jobs like 2 years after and take an assistant professorship at Bentley University. And sort of now we finally settled down. Well, at least like we've been here now for over a year in Zurich with permanent jobs. So like for me, a senior scientist. So I've been working in the field for 10 years. I do applied topology. So the idea of applied topology is that we take ideas from topology, which is a branch of mathematics, of pure math, and then we apply the ideas from topology to analyze data, and people do various things. I'm more on the theoretical side, let's put it that way.
Hello. Thank you for having us at this podcast. My name is Bojan Mohar. As you mentioned, my main current position is at the Fraser University in Vancouver, Canada. My academic career is kind of atypical, I would say. It's less typical than other people who are in outside of Slovenia. So I started with my degree in mathematics in Ljubljana, and I finished in 1979. So that was kind of a long time ago. You can tell I'm the oldest guy in this group. And after I did also my PhD in Ljubljana, but after my PhD, I went to Canada and to US for 2 postdocs. So that was a time when I was thinking, should I stay at home or should I go abroad? And after it was a tough decision to return back to Ljubljana and work there. So I was in Ljubljana all the way until 2005. So for about 25 years altogether. And at that time, I got I was almost 50, so I got an invitation to go to Canada, and it was very tempting to have a new position. It's with a family, with the life already settled at the age of almost 50 years. It's really not an obvious decision to move to another country. So we moved to Canada, and I didn't make exact plans. So I was thinking maybe I will return after 2 years, maybe after 5 years, maybe after 7 years. It's been 17 years so far, so it's still ongoing. However, I keep returning to Slovenia, and I'm spending about 40%, so about 5 months each year I spend in Slovenia. So it's a kind of unique opportunity that I have, that I can live two different worlds. So in working in Canada and still returning home regularly, and work in Ljubljana, where I'm affiliated with the Mathematical Institute, IMFM. And so that's kind of a career and state of the art today. My work is in discrete mathematics, more precisely graph theory, and I do a lot of different problems within graph theory and in relation to other areas of mathematics. I will probably say later when it comes to describe what graph theory is, but it's area of mathematics that became really mature in the last 30, 40 years, mainly due to its applications in computer science. So it's very nice to be in the area which is alive, which is growing very fast, and making it grow by your work. So that would be in short what I can say, answer on your question. Thank you.
Okay, thank you very much. And for introduction, I would like to start with a very simple question. When and why did you make a decision to study math?
So I'm going to guess that I'm going first again. I see my question was a lot shorter than the other. My answer was a lot shorter than the other one, so I'll try to compensate a little bit. So without a doubt, my dad was the largest influence for me, because he always liked math. He would teach my cousins and children of co-workers, everybody. They would come to our home and he would teach them math. And of course, these were almost always students who were weak in math, but he had this infinite patience. And then, of course, he also worked with me, and I just somehow got to love math. And I think it was as early as I was probably like maybe 10 or 12 when I think I fell in love with math. And then later on, slightly later on, I got my first home computer. It was a Spectrum, and that also was enormous fun, and I really liked that. But I always thought that math was real science and computer science was just computers were just a hobby, and I took them to be that way. And that's why I also studied math, even though I was considering studying computer science. So I considered myself very lucky when I got this opportunity to study logic, which, by the way, I was very interested in logic, but we had just one course, a real course on logic in undergrad. It wasn't really present in Ljubljana at the time. So I considered myself very lucky to get this opportunity to study logic at a computer science school, because that gave me an opportunity to combine the two, and the combination works really well. So at some point, I remember a friend of mine when I was applying. So when I was thinking about applying to go to Carnegie Mellon University, a friend of mine told me, you're really dumb, because you're studying math, but you're a lot better at computer science. And he was a computer scientist, and that got me thinking about the fact that maybe I should pay more attention to computer science, and that's how I finally made the jump. And I'm very glad, because now I consider myself both, even though I think my mathematical colleagues think of me as a computer scientist, and my computer science colleagues think of me as a mathematician. But in a way, that's a good position to be in. So that would be my answer.
In my so my mom and dad were both are now retired, but we're both math teachers. And my brother is also a mathematician. He actually works at the University of Ljubljana. I feel it was kind of straightforward for me to become a mathematician in that sense. It's like I didn't have to go through the difficult part of discovering what it is that I want to do. I knew that I was good at math. I liked other things too. So it was sort of like, I really like sociology. Should I maybe study sociology? But then somehow, after many conversations also with my math teacher in high school, I figured that I'm just going to study math, and sort of everything that I went through in terms of courses and applying for a PhD, my brother went through before. So somehow I could see how, what the natural next steps are. I didn't always, more or less, except I guess when I moved to Stanford, that was sort of a deviation. I think at least at the time, most of my colleagues wanted to stay in Slovenia, so it was unusual to decide to go abroad to study. I think that has changed. Basically it was family that mostly influenced my decision.
Okay, so my answer, it's more difficult again. So it's when I was young, I fell in love with science. It was I remember my grade 6 year. I watched a lot of TV broadcasts about science, research in different sciences. That was mainly biology or chemistry and this kind of research. And then I really decided I want to be a scientist. And the area which I liked the most changed from time to time. For instance, when I was in grade 8, I was sure I will be a chemist. So chemistry was my love, and I read a lot of university level textbooks in my grade 8, and it was really something that I admired. And later on, I changed to computer science. So in high school, we just introduced the computer science as a subject, and when I learned that, it was just out of the world. So there were no computers like personal computers at that time, but still it was something that I really liked. And then only in the last year of high school I changed to math. So it was probably I got in the math competitions, and it made me feel that this is something that I really like, and I think it's been exactly the right decision. So I should have been thinking of being a mathematician from very early on. So that's it. Yeah.
Oh, that is beautiful. And Boyan, we stay with you. And as you mentioned before, you mostly work with graphs and graph theory. Can you please introduce us to this field of study?
I'm working in graph theory, and graphs are kind of basic mathematical objects, not like numbers, but like objects which you can somehow work with and research about their properties. And a graph is basically given by a set of objects which could correspond to real life objects like people or houses. And but in graph theory, we just work abstractly with so-called vertices. And this set of vertices, there is a relationship between them. You know which pairs of vertices are adjacent to each other, so can see each other, and they form a complicated structure which we call a graph. So people will understand more if I say this is just an abstract name for a network. So a network is something that you understand what it is. So it could be a network of streets or network of railroads, could be a computer network. Where these objects would be computers, and then the links, the edges between them would be how these computers can interact with each other, maybe over the internet or in some other way. So that's the objects that we work with in graph theory, and it is important that many real world problems can be modeled using graph theory. So you can model, for instance, the problem of finding a shortest path in a network. This is something you see every day when you go from point A to point B. You just ask your phone, or your Google Maps, what's the map they suggest to take, what's the shortest path from point A to point B, and so on. So this is just using graph theory as a model. There are other things that graph theory is modeling. So you can imagine, for instance, molecules in chemistry. You can imagine computers being linked to each other, designing a computer network, or you can imagine, for instance, googling for an information on the internet. So when you Google uses an algorithm which displays the findings, displays the web pages which you might be interested, but the importance is how to rank them. And it's basically the basic algorithms of this are based on graph theory. So it is an area that's been used a lot, and it's gaining importance in today's real world.
Okay, thank you very much for this very nice explanation. And now I would like to ask Sara if you can tell us more about topology. You said that this is something that you have been extremely interested in, and this is the reason why you left Slovenia. So please, could you briefly introduce us to the topic of topology?
Yeah, so topology is a branch of math that deals with shape. I mean, I think that's sort of like the first answer that people usually give. So I have like my 2-year-old is playing with Play-Doh a lot, and what we're doing a lot right now, like we take little bits and then we make different shapes. For example, we make balls, and I taught him how to say Möbius band, and I taught him how to say torus. So he sits in the chair, he's torus, like if it falls off. Anyway, so in topology, we have what we call topological spaces, but like you can think spaces like a torus or a donut or a ball, so the idea is like we want to be able to distinguish between them, but it's sort of but not sort of the invariance shouldn't be too precise, but like there needs to be some flexibility. For example, we should be able to deform the objects a little bit. Like if you have a ball, you can squeeze it just a little bit and it's still sort of, you would say that the shape doesn't change. or you can stretch it just slightly and the shape doesn't change. So the easiest way to think about this, if you go to a game and you see banners and you have you have something written and you can have different fonts, but you are still able to read. So it's sort of the same shape, but just sort of deformed slightly. So topology, so what you do is you study properties of different spaces that do not change when you deform them slightly. So now, there are different ways of doing that. And for example, the class I'm teaching right now is called algebraic topology, which does that by assigning groups to spaces, which are sort of algebraic objects. But roughly, the way you can think of it is, I take a ball and then I can ask basic questions about the shape of this ball, like how many pieces is this ball made of? And it's made of one piece. And then are there any loops in this ball? And actually, no, there aren't, because somehow I can imagine that if I have a loop on in the ball, that I can squish any loop down to a point. And then similarly, if I have a basketball, I can look at the surface and I can ask, how many pieces is this made of? It's made of one piece. Does it have any loops? Well, no, because I can sort of, for any loop that I can think of on the surface, I can squish it, I can deform it into a single point. But then, if I look at the basketball, it has a void. So I would say that it has a two-dimensional void. And this we measure with Betti numbers. So then, Betti 0 number would tell you the number of pieces that a space is made of. Betti 1 would tell you the number of loops that a space has. Betti 2 would tell you the number of two-dimensional voids. And then, in math, when you can get it up to dimension 3, you can generalize it for any dimension. So basically, for any dimension that you can think of, you can say how many voids of that dimension does the space have. As said, if I take a basketball now, with these math terms, Betti 0 is 1 because I have one piece that this ball is made, that this basketball is made of. Betti 1 is 0 because there are no loops on the surface that I couldn't deform into a single point. But Betti 2 is 1 because I have a two-dimensional void. And then if I have if you I don't know, if you wear rings and you wear a ring right now and you take your ring, it's also made of one piece, so Betti 0 is 1. But now it has a one-dimensional hole, a loop, so Betti 1 is 1, but it doesn't have any higher dimensional structure. So the idea is you take shapes, spaces, and you, for example, on the basic level, you can assign numbers to them that tell you something about the shape of this space and that enable you to be able to distinguish between different types of spaces. But then, when you go to university level math, you assign more complicated objects like groups. So that's roughly sort of, I think, about topology. And then, so what I do is, what I described with Betti numbers, so this is the core of the idea about homology. So there are different ways that topologists deal with measuring shape. And one way is to assign these so-called homology groups. The idea was, well, how can we use this invariant that is very useful in pure topology and use it to analyze data sets? And then sort of some problems start because data sets are finite sets. And basically, if you say, how many pieces is my set made of? You just get the information back, which is the number of points. And then there's no higher dimensional structure because it's just a finite number of points. So then you need to make adjustments. And the way you do it is you build what we call simplicial complexes that are general. You can think of them as generalizations of graphs. So like Bojan said earlier, with graphs, we have vertices that are zero-dimensional objects and then edges that are one-dimensional. But if there's sort of three objects that have a relation, you can also imagine that you glue a triangle on top, which would sort of capture the relationship between every triplet, and higher dimensional structure like tetrahedra. And then you sort of assign a family of such simplicial complexes and then track how the shape changes as you vary the parameter, and and then the output that you get is called persistent homology, and is sort of one of the most popular tools for measuring the shape of data sets, roughly. Yeah, and then you can, then there are sort of like various applications. So this is sort of one such method, for example, but then you have many others, and this is then like another tool, along with a lot of machine learning tools that you can use for various data sets, for example, like cancer data sets, etc.
Thank you very much, Sara, for a very nice explanation of what you're doing. And now on to Andrej. So, Andrej, for your doctoral dissertation, you studied computable analysis and topology in the framework of relative realizability, which sounds terribly complicated. Could you possibly tell us something more about your research in more simple words?
Sure. If I start with what I was doing for my PhD, actually the starting point was kind of similar to what Sara was describing, namely topology. Topology, as Sara was describing, is how I learned it. But I then later learned that, in fact, it has a much wider context. For instance, the basic laws that govern topology that Sara studies also govern information. The way information behaves is actually, in essence, at a very fundamental level, quite similar to how topology behaves. And that links up topology with computation. And in particular, what I was studying in my PhD at first was the question of how can we actually compute, so with computers, how can we compute with complicated mathematical objects? So everybody understands that you can compute with natural numbers or fractions, and you can have lists, and you can have bits of data, and any kind of finite configurations. Of course, computers are going to be very good at that. But then if you want to compute, for instance, with arbitrary precision real numbers, so that you are able to calculate as many digits as you wish, that gets slightly more complicated. And then you can ask, okay, but can we also solve differential equations to arbitrary precision? And how do we do that in general? Or what if we move away from numbers and we start to calculate, we want to calculate with points of a surface or something, some such thing, or a vector field. So the sort of things that physicists would like to do, but do it in a precise way. So always make sure everything is correct. Make sure that there are no numerical errors. So that was the starting point of what I did for my PhD, and this took me then to study logic, in fact, because the way the things are organized is that there are several ways that you could approach the subject, and the way that I was studying it is through this realizability thing, which is a way of understanding logic in an unusual alternative fashion. So when we speak, when we make when you have a mathematical statement, you say, for instance, that such and such function is I don't know, that it has a zero or it has a positive zero, and things, any statement in mathematics, usually you think of it as being true or false. But this is only one kind of understanding of what mathematical language and mathematical statements are about. It's, in a sense, the simplest one, because it makes mathematical statements absolute and timeless. So if you say that something holds, you don't ask, it holds forever, everywhere, objectively. But there are ways of understanding logical statements that give you a completely different view of what is going on when you make a mathematical statement. So to give you an example, there are kinds of logic where you have built-in notion of time. So you don't actually, when you make a statement, it's not, you don't ask, is it true? You ask when. So you get a set of time instances when that particular statement happens to be true. So if you consider something like it rains, usually when we teach logic, we say, well, it rains, that's either true or false. Well, but it's not that simple, right? Whether it rains depends on the location on the earth and on time. Both of those at the very least. So one way of understanding the statement it rains is to think of it as a subset of space-time where it actually rains. And that brings in a whole new set of possibilities of how you could do how to understand and what to do with logic. And so the thing that I did was to study what happens when you say, I don't want to know whether things are true or false. I want to compute. I want to have a computation that is witnessing that something is the case. So to give you an example, for instance, there is a famous proof already by Euclid that there are infinitely many prime numbers. And that is a fact. And so you can say it's true. But if you understand logic in terms of logic being about programs, then you're not going to ask, is it true that there are infinitely many prime numbers? Instead, what you're going to ask is, how do I compute that there are infinitely many prime numbers? And then you will say, okay, so I need a program that will output an infinite list of primes. And once such program is established, then I can go, then that is my evidence that there are infinitely many primes. And then you have a particular kind of logic called realizability, where everything is always done with computers. So it's, it really literally is the case that you build a mathematical world where underneath there are little computers everywhere, programs calculating everything. There is no truth. There's just calculation all the way down. And this was my approach in the thesis, was to work first to build such a world. And it turns out there isn't just one. There are very many different programming languages give you different such worlds. And then once you have a world like that, what does topology look like if you do it in that world? What does analysis look like if you do it in that world? Because the world is built with programs all the way down, which means if I prove that a differential equation has a solution, I did not prove in that world. That doesn't mean I proved a true fact. It means that I produced a program for doing it, for calculating the solution to differential equation. Now, there is a long way from this idea, which is very theoretical, to actually being able to extract such a program and run it on a computer and make it go fast. That is a difficult problem. But the principle, I think, is very important, and it's becoming more and more important because it touches on other things like software development, where you say, we're not going to just write programs and hope that they work. We really want to know what these programs are doing. And one way of doing this is to say, oh, but I can view the programs as the building blocks of my logic. And so in my logic, I say what it is that I'm trying to do, and then I can verify that the program is doing the thing that the logic wants. So there are very concrete and important connections here to things like software verification, where we want to know that software works correctly. So in fact, that my work then it goes all the way from these imaginary or alternative or the multitude of mathematical worlds that I study to specific techniques in computer science, where we develop programming languages and other kinds of formalisms or programs that help mathematicians prove theorems. So it's really a spectrum of things. And I really like working in this way, that I'm connected on both sides. I want to see how things can actually be implemented, but I also want to understand the deeper meaning of what is going on and have a really, really broad view of what are the possibilities for mathematics and expression in mathematics. And I think this is actually important because we are in an era where I think computers are about to take over. An important chunk of mathematicians do. And in order for that to be accomplished, we have to have a very wide understanding of what is the space of possibilities that we are moving in, because design of such programs is difficult, and we don't know how to do it, and we need to explore the possibilities. So that's where I see my work. So it can be either something very computer sciencey related to design of programming languages or formal systems for doing mathematics and computers. But on the other side, I also study very general questions in logic and how mathematics works and what are the possible mathematical worlds.
So now I want to turn the conversation to the general importance of math. So I remember from the very beginning of my university what my professor said in the class when we chemistry students were complaining about math. And she very nicely explained why mathematics is not really fully appreciated. She used the analogy of a tray, which represents mathematics. When you serve other subjects, including chemistry, physics, biology, and others, on the tray, people pay attention to things on the tray, but not to the tray. But without the tray, you cannot really serve anything. So, why is it important to research mathematics?
Okay, so one thing is that mathematics is the language of science, right? We all agree on that. And research in mathematics is kind of strange. It's tackles problems which have nothing to do with the real world. So what we do, we go into problems which are very, very abstract. From the mathematical point of view, interesting, but you don't see any application of it. And then years later, somebody comes and says, "Oh, well, this very, very abstract thing which you did, I can do this in my area. So I can model, for instance, how my brain works or something. So I can explain that based on your work. And so this is the beauty of mathematics. What we do, it's we do research which is very abstract, which evolves new mathematical technologies, and then at some point it becomes useful. So that's why I'm usually saying that this is we are developing future technologies which don't yet we don't know what these technologies are, but we are developing them, and at some point our work will be used for those unknown new technologies. So that's maybe a short answer why math research is important.
Sara or Andre, yeah?
I feel especially if you are sort of a little bit closer to applications, there's sometimes the sentiment that, oh, like, not all math is applied enough. And I, at least from, like, I guess being like very deeply embedded in the math community, I do think that a lot of mathematicians don't have immediate applications in mind when they do math. Like Andrej said, it's like, I think it's better than, engineers to think about mathematicians as artists. People work on problems because they really like to work on problems because they're interested in them. And in terms of, and it's, I think not all of the math research will sometimes be used, but you never know with, like you might be surprised then because, you think something, like Bojan said, looks completely abstract, but then you end up, it ends up solving a really important problem. And I think that's sort of like the kind of theme that goes on and on. And in what I do, it's actually also communication the other way around. I work with people in applications, and they have a very concrete problem and they need a mathematical model, and then very often it happens that that model doesn't exist yet. So then it's your job to somehow build a mathematical theory that will model that very well. And surprisingly, sometimes it can be very basic questions that arrive and like give rise to interesting mathematics. So it's sort of it goes both ways. I feel like there is, and I guess recently with a lot of math research, I think math researchers are very good with sharing their research. Like everything appears on archive almost immediately, and is like freely accessible. So like there is much more exchange now than there has ever been. So
So just to elaborate even further on this importance of math and um, these things. So, what do you think? Do you think that we did discover math, or did we invented it?
Oh, discover. I mean, I'm not sure about invention, but yeah, I would say discover.
It's not clear. So if you imagine another civilization, they could have a different kind of math. So it's, anyway. So you start counting 1+1 is 2. I mean, when you count usual objects, this is this is universal. So it's you could maybe come to the same fact with through a more complicated or through a very different way of expressing it, and that would be more complicated in this case, but it would still be a different way of math would be developed. So it's not clear that there is a unique way you can develop math, but it's a very natural way which came to the humanity that they express, and these are universal truths. So it's in math you say this and this thing holds or doesn't hold. It's a theorem. You prove it, and so it's not something that you invent. I mean, it's you invent how to prove it, but these are universal truths. That's my belief. Yeah.
Just tying this question back to your research that you were telling me about before, how would you say that your research impacts our lives?
I don't know. I'm working theoretical math, so it's really difficult to say. The closest I thought I was to an important usage was my work in algebraic graph theory. So you take a graph, you take the adjacency matrix. So this is a huge matrix. You have a graph maybe on million nodes, so you have million by million matrix. You compute eigenvalues, and you say something about the graph based on these eigenvalues. And my work dating back in the 1980s and 90s, so did have influence when they discovered the Google PageRank algorithm. So there was some relationship within my work in that at that time, and discovery of this very efficient search engines. For instance, starting by Google. That was something that I thought it was very close to be in applications. And another thing that I could add is just very recently, I'm looking forward maybe to work with a group of hydrogeologists and theoretical physicists on applying network theory and graph theory to research in karst geology and karst hydrology. So that's something that maybe will make an applied results, which will actually have some so very very high level graph theory results that will make an impact on some areas which are essential for the human society. But otherwise, yeah, it's difficult to say. We all in mathematics, we very abstractly working on with tools which we don't know how they will show up later on.
Yeah, so as I said, I work in applied topology. My field is very interdisciplinary. So there are computer scientists working in the field, statisticians, and then there are a lot of domain scientists. Um, uh, so, um, so like the way I see my work is I have the knowledge of topology and the tools from pure math, and what I have to do is I have to prove that certain methods are stable, for example, and things like that, so that they can be used without too much bad conscience for say analyzing data, and so so far, so most of the projects have been on the theoretical side, but it has happened, for example, like in my thesis, I was working on tropical, like I did a lot of tropical algebra, and then I was approached by a statistician who said, oh, I want to use this on this biological problem. And then, we used it, implemented it to classify some AIDS, HIV patients. And I think in that sense, I do not know, when I think maybe now that I'm, going to be at ETH for some years to come, I will have more opportunity to talk to domain scientists and, see, try to make meaningful collaborations. But it's sort of, like one never knows when somebody is going to come and, take the things you did and, use it for like exciting applications. But just to say, in our field in general, I think one of the most exciting things for me is like, for example, in medicine, because lately there has been a lot of sort of talk about, sort of medicine tailored to the individual. So, like you have like with diabetes, it's like one of the most common diseases today. But, and people talk about diabetes, but there are actually like many different subtypes of diabetes. Some of these methods have helped with discovering new subtypes. And, if say, a particular subtype of diabetes, then you can also adjust your treatment like to that particular subtype to make it more effective. So I'm sort of, like hoping that maybe like in the future, I'm gonna talk more to people that, have a lot of data and, we're gonna come up with something, that would be great, to actually, improve, I guess, like, for example, this determining subtypes and things like that. But we'll see. It's haven't done that yet.
So, all of you now have been mentioning that math has been used in other subjects, and I also used the analogy of the tray before when math is used basically to carry all of the other sciences. But I have a question whether do you think that, for example, new insights can be transferred from other experimental scientists back into mathematics to shape perhaps mathematical dilemmas or I don't know, try to find a different kind of solution to a problem or something like this.
Oh yeah, I think I mentioned that earlier. That has happened to me specifically, that, there was a concrete problem from applications from sensor networks. And then, like we looked at how to model that mathematically. It turned out like, even though, there's sort of like a lot of research done about what's called fibered spaces in math, but it was not sort of to the like not about the not one that would be like, but not the sort of the kind of work that would be applicable directly to the situation we had by hand. So so we had to do it differently. So that was sort of like just one example, and I think there are many more with people who with mathematicians who talk to people from other fields a lot. I think it happens all the time.
Yeah, so it's in math. It happens occasionally that you don't know what the right conjecture is, what the right answer would be. So then you do some simulation using computer, and you find out what's the right answer you should expect, and then you prove it. So it is the use of computers that could be used also in the math research. So that comes very frequently, I think. It's also been the case that some very, very long proofs in mathematics have been verified using computers. And this is what Andrej mentioned before. These are the first signs that computers can do you can program some steps that mathematicians do and be just checked by computer. If there is something that you would need to think for months or years, a computer can do that much faster. So that's there are possibilities like that all over the place.
Okay, thank you very much. And now, Sara, I hope you still have time for your very last question before you need to leave. I would like to ask, how do you feel about the differences between teaching math in Slovenia versus other countries? As you said, you have traveled around quite a lot and did lots of different positions at different universities on different continents. So please let us know what is your impression.
So I was a student in Slovenia though. Well, I mean, I guess I did teach a little bit, but like not very much. Also, my information is old because like I think the math, I mean, somehow the curriculum has changed a lot since I was a student. Um, but at least, I mean, my experience in Ljubljana was very positive. I really liked all the professors. I really liked all of my colleagues. And so I guess, like, I mean, at least comparing to ETH, it seems to me that sort of the structure is very similar. I mean, the students are like very independent and, you know, like they're hardworking. I feel like in the US, I mean, it depends a little bit from place to place, but like students have a slightly different attitude because like you pay a lot of money for college, and then with that comes a little bit of entitlement, you know, like professors really have to, you know, make materials accessible, themselves accessible, you know, provide solutions, like, you know, provide a lot of different things. And then it sort of depends, I guess, a little bit like on the like on what institution you're at. So there is a lot of freedom in deciding what you want to study. Like in Ljubljana, when I mean, at least sort of when you're a mathematician, you take math courses, like mostly math courses. But I don't know, like in the US, if you are an undergraduate student, you can take you know, Greek mythology, and then you can take philosophy, and you can take Russian, and like, you know, you can take you only need to take a certain number of, say, math courses in order to be considered a math major. So then by the time you are finished, you can either know much less than somebody with a degree from Slovenia would, or you could know much more because you would decide to take, for example, graduate level courses in mathematics, which you know, like maybe you wouldn't be able to, like in Slovenia, because like, you know, everything comes at a certain time. Even though, if I understand correctly, there's more flexibility in that sense too. Um, so yeah, so I feel like that it was sort of like like undergraduate um, um, program like is very different in the US, like from at least what I've seen in continental Europe so far. And I mean, and as far as graduate school goes, I feel like I hear like very different things, but most people I talk to really, really liked studying. I mean, like doing their PhD in the US. I mean, you know, I think I would have liked, you know, like Ljubljana just as much. It's just that there are not as many graduate students, and it's really the graduate students that build the community. Whereas, you know, like at Stanford, there was a cohort of 15 people. They all take the same classes when they start, more or less. And you know, like you really spend a lot of time studying together, and you know, it's sort of, you basically make friends for life. Whereas like in Europe, when you decide to do your PhD, it's usually after the master's, and then you already have the advisor that you're gonna work with picked. So often you actually apply to do a PhD with a particular advisor. So there's not, you know, that freedom of, now I'm gonna do a PhD and I have 2 years to, you know, do a lot of reading courses with professors at the university to see what it is that I'm really drawn to, and then only after that commit. So yeah, so I feel like the systems are very different, and sort of each has advantages and disadvantages, and it's probably sort of, you know, like what's better or worse is probably depends on the unique situation that you're in, and somehow like your personality type.
So there is essential difference between this higher education in Europe and US or Canada, let's say, that I feel of. And Sara already mentioned the basic thing, but if you compare Slovenian educational system, it's very similar to German or other countries within Europe, and it's different from US. So in US, students come from high school and they know much less of a general subjects than our high school students learn. And so they need more general education at the university level. And so the university, the undergraduate university level is usually much lower than it would be within Europe. Of course, the two universities Sara and Andrej mentioned, I mean Stanford and CMU, I mean these are the top world universities. So it's not, so they belong to like 10 best universities in the world, or maybe not 10, maybe 20, but this is a different world. So it's a different world. Even the undergrads are better there. So, but and then on the graduate level, there is one essential difference from Slovenia. So there are many more students. So they make a good community of students to work with. And despite the fact that undergraduate curriculum is generally, so in average, it's much lower level than that in European universities, students somehow seem to grasp enough knowledge to prosper later in the graduate school. So in my opinion, graduate schools at these best universities are really just a different world. So it's not because of teachers or so, but it's just because they are much more selected. So it's but if you look at an average American university, so not counting those 20 or 30 best ones, it is not any different from Slovenia, I would say. So it would be probably even a lower level, in my opinion. And so I think, generally saying, I was always very proud on my education in Slovenia. I think I learned a lot during my undergrad studies. And if I compare that to undergrads in US, I mean, it's really a lot. So it's just uncomparable. But the graduate school, that's a different. It's a different answer. So it comes to students are much more motivated, much more hardworking, and so that makes a difference.
Um, and so the next question would be, did you, Sara and Bojan, have the opportunity to return to Slovenia? I know that maybe this is not such a relevant question to Bojan because, as you said, you chose to stay in Canada, and you were not really sure whether it would even take so many years, and now you continue to stay in Canada. But for Sara, have you had the opportunity to return Slovenia, or why have you decided not to return?
Yeah, I mean, I think it's sort of the good conditions in grad school. They continue a little bit throughout postdoc years, and then, it just um, when I mean, at least in math, like when you apply for jobs, you apply for many jobs, like everywhere. And 600, like I think they told me when I was a postdoc that for my postdoc position, 600 people applied. So it's um, there's just like a lot of competition in math. Like there's not sort of maybe as many positions or as much funding as in some other fields. And then you just apply to a lot of places, and then you see where the best conditions are. And at least I mean, I never tried to go back to Ljubljana just because I had like opportunities elsewhere. But I do know that somehow, like in Ljubljana, there have like there have like has always been a little bit of a problem because they're just like not enough. Like I mean, you have people whose title is docent, and then they work as assistant. Basically, there are not enough like senior faculty positions to apply for, and then if you go for a starting position and you are an assistant and you teach for, I don't know, 15 hours a week, you can't really do much research. So I think it's also sort of a question of at what point in your career would you decide to go back. But then, like you probably don't want to do it right after, because then you might get stuck in, a cycle where you just have to teach all the time and you have no time to do research, and then you don't have enough research to show to actually be promoted to, like an associate professor, or then like later a full professor. And then but then what happens inevitably is that people are abroad, and they get positions, like one position after another, and then at one point they get permanent positions, and then like you have a permanent position in Switzerland, with like very good conditions and like family and good salary, and then it's like, well, am I really going to move the entire family now to go back home? And we don't have that planned. I think maybe when we retire, but like for now, I think just like with Bojan, we spend a lot of time in Slovenia because the semester is like 13 to 14 weeks, and outside the semester, like we can also work remotely because we don't have labs in math. So I think that's sort of a good alternative to actually working in Slovenia.
Yeah, it's for me. It's not a big deal. So I think I never asked, but I think if I wanted to really return, they would probably take me back as a professor at the math department in Ljubljana. But it's just a lifestyle that I have right now. That at the moment I don't want to stop the way I'm doing. So I have so many research projects, and just returning to Ljubljana would probably be changing this course a little bit.
So you touched a bit on the research environment in Slovenia and how it compares with other countries and such. And how is it with fundraising in Slovenia for research as compared to other countries? And how is it with, for example, cooperation with companies or any kind of international connections? How is this for particularly mathematics department?
So one thing I'd like to mention, just to answer the question about connections with industry, within Slovenia is in some sense too small. So when I came to Canada, I was really impressed. It's a difference. So like I was kind of regularly, maybe twice a year, contacted with people from different areas. So they would come, people from brain research contact me. There would come people from other applied areas contact me, and it's so much more activities that you can collaborate in comparison with Slovenia. So Slovenia is really small. It's a small, altogether it's a small city, 2 million. It's a small city. In China it would be a village, right? So it's and then we have some very strong areas. We have some strong industry, but it's limited. So you show your fingers and you can almost count this. So or maybe it's 100 instances of that. So it's not a big room. So we need collaboration across borders. That's my message. So that would be much more. And the European Union is just doing like that. So this networking funding from European Research Council, all that is going this way.
Okay, for my second to last question, question. I would like to ask, in which math subfields is Slovenia strong, and what can be done to strengthen our position further when we compare Slovenia to leading countries in the world?
There are some traditional branches which are very strong, like, I think complex analysis is doing really well. Graph theory is going very strong, even though Bojan is not around anymore. I think we have had some success with the other kind of theoretical computer science that's surrounded around the sort of things that I do, because we have a group of people working on programming, theory of programming languages, semantics, things like that. It's maybe a bit hard to judge myself, so I can't really tell what the influence is there. Bojan, who am I forgetting? So maybe the general idea is that we have these groups of people form. They're not very large groups because there aren't very many of us, but groups of people form that then are quite successful and maybe can go on for several decades, and they contribute something. We have good group theorists, we have some young group theorists even, so that's very promising.
Yeah, I think as far as I understand, so the Slovenian Research Council is supporting 6 research programs in mathematics. And so basically all of these are doing well. So it's Andrej mentioned graph theory and theoretical computer science. There is algebraic and linear algebra, topology. I think and then analysis, of course. So we are covering a broad spectrum. Of course, not everything. I mean, it's only 6 sub areas of mathematics. But whatever this in these areas, I think the Slovenian mathematics is pretty good. Yeah.
So to mention some that we don't cover, for instance, number theory. We don't have much number theory. Algebraic geometry, I think now we are actually without probably any algebraic geometers. So there are, of course, areas that we do not cover, and it cannot be expected that we would just cover the whole thing. I mean, no single university on the planet does that anyway. But the ones that exist, I think it's fair to say we're good we're at least very solid, if not good or very good.
I would very much agree. I think the Faculty of Mathematics holds the best faculty at the University of Ljubljana, if I'm not mistaken.
Oh, if you're looking at statistics, you have to be careful to separate physics and math there, because the typical academic statistics, the bibliometrics for physics is I think in general higher than for mathematics.
Okay, I did not know that. Anyways, we would like to thank you very much for such a great conversation. And before closing, are there any resources such as books, articles, podcasts that you would maybe recommend to our audience that would be further interested into exploring math?
Well, I can recommend some of the some new stuff that does not exist on paper. So a member of our research group, Egbert Rijke, is a postdoc from the Netherlands. With co-workers around the world, has been doing great things in providing teaching material in the area of type theory and homotopy type theory, and things around it. Things surrounding formalization of mathematics, that is to say, working with the proof assistant, working with a computer when you develop new mathematics. And if you look him up, you poke around or contact me, then they had a successful online summer course. Everything is recorded on video. There is a lot of material and exercises and everything. And I think they had 2,000 students during the summer. So that's a good number. So that's one thing I can think of that I can recommend.
I think there are many online resources nowadays. I generally don't have time to spend much, so sometimes I read from time to time. I read an article from Quanta magazine, so that's a popular science magazine. So it covers kind of recent developments in mathematics. in particular, also in other sciences like computer science, physics, and so on. But it goes the way to trying to explain even the hard achievements done in mathematics in a way that people can understand. So Quanta magazine, it's an online thing. You can go there and check.
Right. I joined that recommendation. It's yes, it's got good stuff. Here's another thought. If you are a sort of a student or a younger person and you're trying to find out what's going on, maybe somewhat surprisingly, you can find out a lot of you can find out about what's going on and who's who, and just follow discussions of all things on Twitter. Amazingly, there are these mathematical sub-communities on Twitter that just discuss math. I mean, occasionally they succumb to all the bad things that happen on Twitter, but they're doing really well, I think. So that's one public source where you can begin to find out what is out there, because as Bojan says, there are a huge number of online resources available. But I've noticed that people have been, for instance, random people have been contacting me also through Twitter, for instance, and asking questions. Seems to work.
Well, thank you very much for your recommendations, and thanks again for such a great conversation.
Thank you.